All right. Hi, everyone. Thank you for joining to VSA Online. Today, I have a pleasure to host a talk by Thomas Ahl from Normal Computing. So, without any further delay, so I leave floor to him. So he will probably tell a few more words about himself. Thomas, please.
Yeah, hi everyone, and thanks for tuning in. So, uh, Jenny invited me to talk about this work that I did while I was at Meta together with Henry Tsang. Um, and um, this work was intent is about taking these very large embedding tables that are common in a lot of different systems in machine learning and computer science, and finding new ways to compress them, thereby saving, of course, like particular communication overhead. And we thought there could be some overlap with the VSA community and in some of the techniques and the interpretations of some of the techniques, and also just in the application, since you obviously, when working on any kind of vector symbolic architecture, you need to store a lot of vectors, and so maybe this can be practical for you guys. There is a website also for this paper that links, well, both to the PDF. It also links to a GitHub source repository, where we have implemented this method together with 12 other related methods. So if you're interested in using some of this in practice. Um, but yeah, and right now I'm at Normal Computing, which is a company that does like a startup in New York and Copenhagen, that does AI for hardware with a verification of chips. Maybe I'll just give a small plug about that at the end. But the motivation for these embedding tables is very wide. I mean, obviously, we all know them from token embeddings and so on in transformers, but they're also common for anything like working with any kind of discrete data, right? Like user IDs, item IDs, and a recommendation system, and so on. Like if you have a graph neural network, like at some point, you need to embed all the IDs at the bottom level before you can even start to use your neural network. So like if you have some typical click prediction architecture, like we used at Meta, you might have different features for like IDs, like uh, this could go from 0 to 3 billion, or how many users they have now. There's one for country that probably is smaller universe, but there are gender ones. There could be a sign up date that could be even bigger than the number of users. If it's a movie we're interested in, there will be a movie ID. All of these, each of these IDs then get looked up in an embedding table to some vectors of some high dimensional size, and you can then put these vectors into your neural network or your like VSA algebra, and do everything you need to do. At the end, you get some value out, and of course, um, you're then going to train like these vectors. You'll find out by doing sort of end-to-end training of your neural network that also includes the embedding tables. Um, but yeah, these embedding tables can be really big. So of course, at Facebook again, there are like many billions of users. So if each of them need their own vector, it could be a lot of like if it's Twitter, like you want to make a recommendation system for what tweets to show somebody. If each of the tweets need to have their own vector, they have like 10 billion, I think. Maybe it was 100 billion. Maybe I missed the zero on this one. Um, Hundreds of billions of tweets every year, or like at a token embedding system like a transformer like Llama has. Um, I think they have 128,000 tokens. Wait. Oh, yeah, okay, there's a number wrong here. But I think Gemini has like multiple million tokens. And each of these vectors again will have like in the transformers, for example, will have thousands of dimensions. So um, you can easily have one of these embedding tables can be many terabytes large, even like compressed to a pretty small number of bits per parameter. And then again, if you had the previous system, we had multiple different features for our input, and each of those, if you have 1,000 different features, you need 1,000 of these embeddings tables, and now we're up in thousands of terabytes. And the main question is always, do we really need that many vectors? Like, surely there is some similarity between some of them. There's some sharing we can do, and maybe we can convert some space to computational time. Like, maybe we are okay with using more processing time if we can use less space. So that's what we wanted to look into. And these are like the four, or like, well, three previously known methods, and then how they relate to our method. So the most basic method that many of you probably are thinking about already is like the hashing trick, where you just say, hey, we have all these IDs, a billion IDs, but we only want to store 1,000,000 different tables. So I think everyone learned in like machine learning 101, you just take a hash function, you hash down to 1,000,000, and then people, like different concepts, will just get the same vector. Somehow things often still work out reasonably well. I guess it's a bit, why would it work at all? It might be that some of these vectors, some of these IDs are not used very often. So I guess it'll probably be that the most important IDs end up dominating the value in the bucket, and the other IDs don't really, they just kind of end up being noise. But it's pretty rare that you need them, so maybe it's okay. But it's not a very satisfying solution, obviously, when you can't give every ID a unique vector at all. Like, so your neural network will have zero chance to distinguish them. There's like one improvement over this is called sum hash embeddings. Basically, now you have two tables. If we want to use the same amount of space, we can say they have 500 rows each. And you have two hash functions. So each ID will map into to a bucket, and then, well, to two different buckets, one in each table. And then whenever you want a vector for an ID, you just apply both hash functions. You take the two vectors out and you add them together. So I guess this is what in VSA you would call a superposition. So you're basically trying to represent all of your different concepts using some superpositions. And of course, now you basically get like you're able to represent like the square number of concepts than the row in your tables. So this can be, so basically, as soon as you have two tables here, you can probably give a unique vector to every single concept. A similar method is, there's a paper called compositional embeddings, which is partly what we saw originally and wanted to improve upon. That's why our method is called clustered compositional embeddings. But it's a very simple idea, really. It's basically the same as some embeddings. They just do different columns instead. Like they concatenate the vectors instead of summing them. There are really a lot of papers in this area that have very simple ideas. Yeah, and test them against each other. I don't know if concatenation is so common in VSA as an operation, but I'd be happy to learn more if it is. In practice, it just seems to work pretty well. So I think, yeah, I mean, of course, if you just added all of these, you could just learn, to have zeros in some of the columns, and you could represent everything you can do with concatenation, you can represent with sums, but then you would use more space. So if you want to use a fixed number of parameters, at least, it seems concatenation is sometimes better than summing. Anyway, our method also uses this concatenation, but the most interesting part is the summing part. So basically, in each column, we do the sum hash, but we don't pick the hash functions at random. Our goal was to say, can we when you're trying to say like some user, like you're trying to make this composition of superposition. So you're trying to represent, maybe it's some movie or something as a superposition of two different concepts. Um, why would you choose them at random? Like it might be that two movies that are more similar should really be sharing at least one of the concepts, or should be sharing the vector in one of the tables. Um, so ideally, if we already knew the vector for every single concept, this would be just a simple, k-means clustering problem. But of course, the problem here is that we don't like the whole goal is to try and learn these vectors, so we don't know them in advance, and so we can't cluster them because at the beginning we don't know what concepts should be similar at all. Um, so we want to somehow learn this hash functions of the sum hash embeddings. We want to learn it as in part of training our end-to-end neural network. So that's the main goal of this algorithm and this talk. Please stop me and ask questions at any point if anything is unclear. Okay, so how do we do it? The idea is that, well, as I said, we start with basically the same as the sum hash. So in this picture, all the blue circles at the top, they're the concepts that we're trying to embed. And we have these two tables, and you can see every concept is hashed to one vector. The vector are these orange squares. So each concept is hashed to two different vectors. And at the beginning, they're all orange. This just represents that they're like zero initialized or like random initialized. Now we're going to train the neural network, as I said, like end to end for a couple of iterations. I'm not showing the whole neural network here, so really that should be like some arrows from the blue concepts maybe that go into the network. But we're going to backprop all the way through the network, and at the end we're going to put some values in these vectors that are basically what you would do with the sum hash embedding. Like you would just learn what should each of these vectors be to give the smallest loss at whatever downstream task you're doing. But then the interesting part comes, which is that now we're going to cluster. Now we're going to apply clustering because now we actually have some idea of similarities. So at least like in the simple version of the algorithm, we would now actually materialize all of the vectors for the concepts. Basically like go through each of them and then compute its vector as this sum. And then when we have this huge table with all of these vectors, we then apply clustering, like k-means clustering, like we said, and we get, a smaller table here. Maybe we get these 4 vectors if it's like this very small example. And most importantly, we get some special assignments. So here the colors basically represent like the mean, like the mean color in like some color space. So it turned out that by this process of backpropagation, these like concept number 3 and 4, we found to be pretty similar. So now, so they ended up being clustered together. Of course, we don't like, this is just the first iteration of the algorithm, so we might later change our minds about this again. But at least for now, this seems like a good choice. And then because we want to do this like multi-iteration thing, we now initialize the second table again with random values, but we pick a new random hash function to sort of gives us the opportunity for exploring, new combinations of combining things. And then we train this again. So, and every time we do a circle in this loop, we get a slightly, because we now have, we have a better hash function, which means we can learn a better vectors up in step 2. And that means the clustering in step 3 gets better, and so on. Does this make sense?
Do you refine the old clusters as well, or you don't touch them? I mean,
Um,
the previous
yeah, we train everything again. Yeah. So both the old and the new table. And sometimes we experimented a little bit with how exactly to best initialize the new vectors, or in step 4 to give the least sort of discontinuity in the training. Um, but it turned out to not matter too much.
Okay, thank you.
So okay, so yeah, so in practice, this is we can see this is like a data structure um, where you first initialize your two random hash functions. Um, you initialize these tables with random values. You can see here, like the D1 is like the universe of the concepts. So like, yeah, it's where we're hashing from, and K is the size of each table. And here D2 is the size of the embedding vectors. So we have these M1 and M2 of the tables. They each have K vectors of dimension D2. And then whenever we want to get one of the embeddings, we just, again, like here, I think you should just, maybe you just ignore the concatenation part. The most important part is this, that you look up with each hash function, you look up the ID with the first hash function in the first table and the second hash function in the second table, you add them together. So it's very simple, very fast. And then whenever you want to do it, whenever like you're gonna try and there's a little bit of decisions to make and how many iterations you're doing, and like how much you're gonna train before each step. But then you again here you in this first line here at T, we are gonna materialize all of these vectors. And then we compute the k-means, and we take the assignments we use for instead of this first hash function and the centroids we use for the second one, we pick a new hash function. And the second one here, we just zero initialize it. So this is just the same as what I had in the previous slide, but written in pseudocode. So I'm going to show some more theoretical results in a bit, but just first here, the experimentally, this works really well, as you can see. So we tried this on this big data set, the movie lens data set. And we compared this with these other methods I showed you, like the hashing trick, or just like the simple, like the compositional, like column-based embeddings. And we found that we could get like 8,000 times compression over the baseline model. So basically the original, like if the original model that just had, vectors for like individual vectors for every single concept was like completely over parameterized, which we can also see in the fact that we were actually able to, if we then made our tables a bit bigger, we could get a better loss even than the baseline model. Honestly, like even all of the methods, like the hashing methods and so on, also were able to beat the basic model, which again shows that the basic model was like very overfitted, but there's still like, you see this is like log scale, so compared to like the hashing methods, so these other methods, we were able to compress it a lot more. So okay, so then we wanted to understand a bit more like what kind of guarantees you could get with this approach. Like we didn't want to just have something completely heuristic. We wanted to have to understand better what we were really converging towards when we did all these iterations, and how many iterations we needed, and so on. And basically the way we think of it is a sum of this like online codebook learning, where well, and we wanted to analyze it in like just a simple case, like a least squared optimization. So in this simple problem here, you have this matrix X, which is all the data, so it's like a ton of rows, because it's all the interactions you have between your, like, for example, your users and the movies or something. For the movie recommendation system here, we have like 10 to 15. Of course, this is, so it's also done in in multi batches and so on. And here the D1 again is the universe. So for some of the large examples we had, it was like 10 to the 10. So this is obviously this is very sparse also. So it's with one per column. You could say it's a little weird too. I don't know if you guys are okay with representing this kind of thing as a matrix, but it's really, you could also just represent it as like n many IDs. But representing as a matrix, we can see there's this least square problem where the middle part here is like a codebook a representation of the model, basically. So if we weren't using this model, this representation HM model, this would just be like the coefficient, and so we're trying to find this matrix that minimizes the distance to these labels out here. But we're like this again, it would be very large, like this embedding table. So we're going to try and find it as this decomposition in terms of a sparse matrix H and a small codebook M. So as some of you might be used to thinking about things these ways, but some might not. But you can always think as k-means clustering as a kind of matrix decomposition, where you're basically representing all the assignments as this sparse matrix, which is like the H1 row on the left, and we have a small codebook, and so we're picking out different rows. And if you add 2 ones to each column in this H matrix, it means that you're picking out 2 rows and you're summing them together. So we're trying to solve this simple least square problem, but we never want this HM matrix, which is the embedding table. We don't want that materialized at any point. We want to learn it directly in the form HM. But we would like it to be similar in quality or in, like, we want this loss that we end up with when we do this problem to be similar to if we had first learned like the full embedding table and then compressed it. So yeah, again, is this like roughly, does it kind of make sense? This representation of the problem.
Yeah, makes sense, absolutely.
Great. So yeah, so now again we can write this algorithm out in pseudocode. So in this case, again, we do like the materialization by multiplying these H and M matrices, and we run the k-means. And here we pick we pick this random assignment, and line 7 here we concatenate the assignments with the random hash functions. That's like the step 4. And then in line 8 we do the retraining where we solve So basically here we can just use like a normal least square solver, because we can multiply together this XH part, and then we have like a very small least square problem to solve. We find the best codebook, and we can reiterate. So this is the algorithm we wanted to analyze, like how many iterations does this take? And it turns out that this, well, at least for now, I guess the slide is just showing experimentally, like it does actually work. So when you iterate this process with k-means, you get, so, okay, let's think about this. So the blue line here is what I said before. The blue line is the loss when we pick like X and Y just at random, and we just solve the least squared problem, and then we do the factorization using k-means, so it's basically the best we could hope for in some sense. We got this the blue line here, the blue loss. But actually then, and so after 200 iterations or so on, we reached that level. But then we actually got better, which I guess made sense because we didn't our algorithm was able to choose 2 different locations. So we had a little bit more representation space, since we did this like a superposition of 2 concepts from the codebook instead of just 1. So we also tried to use a more fancy version of k-means algorithm that does this, that finds two different that finds the best factorization in terms of like a two sparse H matrix and code book. And it got this loss around 300, but then when we ran we had to run it like a lot longer, the algorithm, but then it was actually able to also achieve that loss. So, okay, so then we were pretty convinced, at least when we saw this, that it seems that this algorithm really does work, like using this, which was kind of cool because, yeah, it could easily be that it would just sort of maybe improve things a little bit, but then start to just go around in circles and not find anything better. But now it really seems like it does find the optimal value if you run it long enough. And again, it uses it uses way less memory than these two other approaches. So okay, so we weren't completely smart enough to analyze that version of the algorithm. We had to analyze slightly slightly different version where instead of using a random hash function in this H matrix, we just use like normal distributed random values. We think it still should have the same properties in terms of the linear algebra. It sort of just needs to have like a lot of entropy for this exploration thing in line 6. But using this slightly modified version, we were able to prove this theorem that basically assuming also a little bit that X is not like that the sort of the stable rank of X is not too weird. Things will have this sort of exponential, like we get this exponential decrease in the loss. So in this sum here, so it says like the expected loss after I steps is this value that decreases exponentially in I plus the loss of the optimal solution. And again, we could also, when we actually ran this dense version of the algorithm, we could also see that it converged like really fast. Like basically, it actually, so in the plot up on the right, you see that the theorem was actually even like a little bit too conservative. So it seemed that this green line is when we don't have this precaution about the conditioning of X. And we actually said, it seemed like we could actually ignore it. I guess we just weren't able to analyze it without using that. But then this basically shows that you have like a very reasonable number of iteration that just depends on the size of the universe divided by the size of your code book. And actually, if you see like how much faster this algorithm on the left is compared to the optimal one, you end up that they actually have the same running time. It's only that this dense version uses way less memory. So like, yeah, they're like, and the number of like each iteration of this one is exactly d1 over k times faster. So it makes a lot of sense actually that should be the number of iterations it needs to achieve the same quality. Otherwise, we would have found like a much better algorithms for doing least square problems, which was never our intention. We just wanted to reduce memory. So yeah, so in summary, we found this approach, like we found this method where we could actually take clustering and integrate it into like a continuous training pipeline of a neural network. And this was something, I mean, there's a lot of theoretical work on this kind of learning to hash and optimizing hash functions, but this is the only work that we know of where it's actually like competitive and practical. Like other times it would often require you to like you get at least like a size of the universe factor overhead or something. Sometimes it's like cubic in the size of the universe, which is like completely impossible for us to do. And Yeah, so this is, of course, it's only really useful if your embedding tables are very large compared to the rest of your model. If your neural network is much bigger than your embedding table, maybe you don't need to think about this. Um, but yeah, we also found it very nice with the theoretical results. Of course, all the proofs are in the paper. As you saw, there are also some open problems and in removing some of these assumptions that we made. We'd be very interested if anyone is have some ideas for approaching that. Um, and yeah, we also published this GitHub repository with 12 different compression methods for doing this kind of work. Some of them are these two cute ones. Some of my favorites are in terms of tensor decompositions, which we can show via tensor diagrams. There's like one is called tensor train decomposition, because I guess you can kind of see the structure there on the right, how all of these you use these like order 3 tensors and you string them together. Another option is like a low rank tensor decomposition, which is very similar to, well, both of these actually are very related to the tensor sketches. If you saw Rasmus Pag's talk about that. I think this low rank tensor decomposition, you can also see it as, yeah, as I said here, a Cartesian product of element-wise products between. So you have multiple tables and you multiply together all the pairs or all the triples. You get a much bigger table out. So yeah, that was my talk. And yeah, then any questions?
Thomas, thank you very much. Great talk and definitely useful in our context. Yeah, so we have questions here. So let me see who raised. Mary.
Uh, do you think that you're talking particularly about an application to recommender systems? Have you thought about potential applications here for perceptual classification in some kind of agent, such as discriminating between meaningfully different kind of stimuli in the environment? Is that potentially also another way this could be used?
Yeah, so when you think of discriminators, I'm wondering if you mean also like often you have, I guess, at the very top of a neural network or something, you have this big like softmax layer or something. And some like if you want to classify between a lot of different concepts. And that's so that it's basically the dual, I guess, to the embedding where you go from all these concepts to a vector, and at the top you go from a single vector to a discrete concept. And yeah, I think it's actually very possible it could be used at the top as well. I don't know if that's what you mean, or maybe I misunderstood.
Yeah, yeah. I was just thinking like kind of those softmax layers you're talking about, they're potentially very, 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 very big.
Yeah.
Um, so you might want to make those smaller as well.
One difference there is that at those softmax layers, you typically need to basically compute, you need to compute the inner product with every single vector in order, yeah, to find, you want to know which one you have the largest inner product with. So there's also like a big computational bottleneck there, whereas for the embeddings, it's just the lookup. So the computational side is very small. So it's yeah. So that's just to say that that's another potential benefit of using some kind of structured embedding table, is that you might be able to do that like nearest neighbor search that you need in the softmax more efficiently.
Thank you.
I have a small question on my own before I pass the word to other in the audience. The size of the code books, I'm not sure, maybe I missed you commented on it. So this K, how do you select it? I mean, is there any optimal value of it?
Yeah, so I guess the K, well, in the more theoretical work like this, I guess the K will you're just gonna get a lower mean squared error the bigger the k, because you're able to represent sort of the true minimum more and more precisely. In the more sort of empirical case, you saw we had this effect that actually it's not completely monotone. There is actually like an optimal value for k here, at least if in the types of models that we were doing this on, because I guess if you allowed the embedding table like too many degrees of freedom, you would end up getting sort of an overfitting problem. So here we used like a validation set, and so we tried. So here we did one clustering iteration for each epoch. And we trained this model for 10 epochs. It's a big model, so we couldn't afford to train it for more than 10 epochs. But then we just stopped at the validation set, like when it started to overfit. And so that's how we knew. Well, yeah, I guess actually, sorry, this is slightly different, because that's how much you should train it. Yeah, and then we got here the number of the parameters on the tables is the x-axis, right? So then we could just kind of see, depending on what loss we wanted. Like clearly we didn't want to put it more than around 10 to the 4. But if we wanted smaller, we just had to live with some kind of worse loss. And in some sense here, actually, we weren't really trying to get a better model. We were just trying to match what was already there. So then we were really just looking for this intersection point with the dotted line.
Yeah, thanks. Dmitry, you
Yes. Thank you, Thomas, for your very interesting talk, both theoretically and empirically. And simple questions. And what is the sense of that big Y matrix or vector? Is it given by a teacher to fit it? And what is the sense of this? What is there?
Wait, what do you mean, like how do we get the vectors?
I mean, the Y vector or matrix, big Y, in your algorithm.
Oh, sorry, I see this one.
Mm-hmm.
Yeah, so in this case, we were analyzing this as just being this linear least squares problem, right? For the theoretical part, we were just assuming like the y's are just like the labels. So it's just I guess it's called multilinear regression, or like, well, basically the labels are small vectors.
Yeah, but the labels are given by the teacher.
Yeah, it's part of the input in this very of the problem.
And what is the sense of is the meaning of components? Does they have some meaning?
Yeah.
Some probabilities or no?
Yeah, okay. So yeah, I think that's a good question. So when we try and represent all of these concepts, with using vectors in the neural networks, it is very interesting what the vectors end up really meaning. I mean, we obviously have some idea that concepts that are similar in some kind of semantic way, or they should be closer to each other. But that's really the only assumptions that we make. I guess, I mean, sometimes, if you want to have more interpretable features, you need to use some sort of sparse embeddings, or bottleneck layers. Or you can use, some of these like, sparse autoencoders or something to try and like detangle what's really in there. Because probably in a lot of these cases, it's kind of rotational invariant. So like the neural network or wherever you get the outputs from doesn't really care about rotations of your vectors, for example. So that means everything is probably like messed up in some sense. Like you can't, at least the individual numbers themselves don't have a lot of meaning.
Okay, thank you. And did your big M matrix, it sometimes I saw it is initialized as Gaussian variable and sometimes as zeros.
Yeah, I think here do we initialize it zeros? Or maybe here. So I think we kind of it's a little bit like I think it just doesn't matter so much. So the thing is, when we do the theoretical algorithm here, we don't even need to initialize it, right? Because we just call this linear solver black box that just gives us the right M given the assignments. So it's only really when you're using this data structure formulation where you're doing this kind of online in part of the optimization that you might want to initialize M somehow. And I think you mostly just want to, again, like you're going to change M very soon. The important thing was like finding uh, these new assignments. You want to have like as little of a discontinuity, like because if you put something really crazy in M, then like also I guess in this part part 4, then suddenly all of your concepts have some vectors that are very different from what they had just before you did the clustering. And that might give you like instability or something in you're training your model. So that's why we sometimes use 0, or sometimes we just try to compute sort of the residual, the average of the residuals of like whatever value would just like create the least disturbance compared to step 2. But we didn't really find that it mattered. So yeah.
And so to training, I think you mentioned what solver do you use? You mentioned backpropagation at the beginning of your talk, but
Yeah, so say we assume that we're using these vectors for something that go into some kind of training process that already existed. Like we assume that somebody's already training this embedding table as part of a bigger neural network that has some labels and some loss function. And now we just pull out that simple embedding table they used before, and we put our sort of little data structure in to replace it. But that means that we still can do like the normal forward pass, and then when you do the backward pass, you get some gradient for how it should update the table. And when you're doing something like a sum, basically just both of the vectors will get the same backprop, the same gradient, right? It'll just be copied to them.
thank you very much.
Yep.
More questions? Tony.
Yeah, yeah. Interesting stuff, Thomas. So what you're doing here, it seems like you're looking at ways of representing the code book with vastly fewer bits.
Right.
Right. And so I wonder if you tried other ways of doing it and compared them, like using lower precision on the individual vector elements. Yeah, because it looks like you're using floating point or some kind of decimal format for the vector elements. You could, if that's 32 or 16-bit floating point, you could quickly, reduce the number of bits by going to much lower precision.
Yeah. But also these lower precision methods we can also still use in our representation.
Right, and compress them further. Yeah, yeah, and I mean another obvious way of using fewer bits to represent the vectors is just to have lower dimensionality. Did you
Yes.
did you do any comparisons there? Like, if you compress by a factor of 16, which I know is much less than what you said you got, but compare that to the same system with vectors that are just 16 times low dimensionality. Did you try anything like that?
Yeah, so we do have in this code base thing. I did also do this low dimensionality thing, and it did actually work very well. Basically I just used the full embedding table of like say I originally wanted to use 100 dimensions, and then I used maybe 30, and then I just also learned a vector, sorry, a matrix that would like project up from 30 to 100 or something. So just, just so I could plug it into the same model. I didn't count that little matrix from 30 to 100. I didn't count it as part of the budget. And at least when I wanted to just cut the size a little bit, it did work very well. But part of the issue actually was that some of the main vectors we wanted to test, there were only 16 dimensions wide already. So in some sense, the engineers, they had already been trying to squeeze these things down as much as they could. So they were already using vector quantization, or like not, yeah, I think how many bits were they using? Maybe they were using 1 byte. I think they were probably using 1 byte per parameter, but then they were using 16 dimensions. But that meant that we, by trying to reduce the dimension even further, both had that avenue already been sort of explored, and on the other hand, we wanted to get more than 16 times compression. So we knew that even if we reduced the dimension to 1, we would never get close to these other numbers. So like basically the other papers you see, they were already saying they could get like 1,000 times compression. And of course, yeah, so we ended up getting more than that. But if only decreasing dimension couldn't have gotten that far. But in some cases, actually, does seem to be the best thing to do. There are a lot of more experiments on the GitHub for that.
Right. Okay. Yeah, it almost seems like if you can achieve this really high degree of compression, it's like it doesn't. I'm wondering. In some sense, that seems to indicate that the dimensionality is a lot higher than what is needed, but for at least for the representation of the embeddings. But maybe there's something about how they're manipulated that still needs that higher dimensionality. And could you build that insight into an operation in the network that allowed it just to work with lower dimensionality embeddings, but expanded it where in the place in the network where it was needed?
So the way I'm thinking about it is, say you have like, again, 1,000,000 movies or something, right? And maybe 100,000 of the movies are completely different. So they have like maximal entropy. But then the other 900,000 movies are very, very similar.
Yeah.
So all of their vectors should basically be nearly the same thing. They still have a different ID, but maybe it's actually just duplicate data somehow. Like, then we can't really expect to be able to reduce the dimension so much because again, like there is that big group of movies that really do need it, but we would really like to be able to identify this similar part and not have to store them with separate vectors.
Right. Okay. Yeah. So you're sort of saying that for representing the semantics of the space, you do need the dimensionality, but not all the instances need that full information.
Right. Yeah. If we somehow have a lot of duplicates, you could at least our methods would ideally find them all and just map them to the same vector.
Yeah. Okay. Okay. Interesting. Hey, I just have a quick question about this very slide you've got up here. I'm not understanding how this is 8,500 times compression. It looks like it's going from 10 to the 6 parameters down to 10 to the 3 parameters. So the whole table is 1,000 times, data storage difference. So how is that 8,500 times compression?
I think because the dotted line actually uses more like 10 to the 7 or something. Like I would have to look it up.
Okay.
I guess we just it was very expensive to run the experiments with that large table. So we only, and it seemed like the pattern had kind of emerged at this point.
Okay. Yep.
That's a good question.
Okay. Thanks.
Yeah.
All right, let's check if we have more questions. Anybody?
This is wrong, by the way, where it says movie lens. This was actually this Kaggle criteria data set. It's a different one. It's a larger data set than the movie lens 100 million. I don't know why I just miswrote that.
All right. We are quite on time, I would say. So if there are no more questions, so now it's a good time to wrap this webinar up. Thomas, thank you very much for your talk, and definitely it was really relevant. And so we just
Thank you for inviting me. It was a pleasure.
absolutely. So, and
was-
I hope you would be available even to give a talk on this graphical tensor representation. So, which, yes,
Yeah, I'm writing a book on tensor networks called tensorcookbook.com. It's only a draft for now, but
yeah. Yeah,
it's
but I would like to know more, even in our context, of how to represent, manipulations with vectors and matrices and some graphical formats. So, all right. Thank you all for joining us today, and thank you once again, Thomas. So see you in 2 weeks from now. Thank you all.
thank you.
Bye.